yeah, today I'm going to talk about the machine infrastructure cost in Kubernetes. The agenda looks like this. We are starting to talk about the cost drivers on Kubernetes, what countermeasures we can start applying to kind of manage those, some trade-offs that at some point we have to take, some tooling in the cloud native landscape that we can rely on. So starting, the cost drivers. So yeah, where is my money going, right? Today, I'm not going to talk about costs related to cost opportunity or money or people or deployment systems. I'm going to focus mainly on Kubernetes and the infrastructure around Kubernetes. So yeah, bear with me. I'm going especially to talk about in the cloud, right? Because what in our experience, what we are seeing is most of the cost drivers that are that our customers are dealing with is based on these three areas: computation, traffic, and storage. And this is really related to the cloud because on-prem, as I will show you just in a few, this is a complete new whole setup of cost and drivers. So it's not going to really match with what Kubernetes probably native tooling will help. So here, the computation. Let's start with CPU memory. How to manage CPU memory in Kubernetes? How to manage traffic, ingress and egress traffic, and storage. Different types of storage, the size of the storage, how it's related to the cost, and the different use. So depending on the throughput or the input/output, you will have to pay a different amount of money, right? So as I said before, on-prem is not touched here because there is a whole setup of different cost drivers that are not really related with Kubernetes, like design or build your own data center, hardware licenses, power, connectivity, maintenance and upgrade, a different kind of set of intangibles. So we are going to focus today in the cloud, especially because the model is paying based on what you consume, right? And even some of the players on the on-premise world are trying to move to an hybrid scenario where you can pay depend on the hardware that you use, and you can grow easily. This is a different scenario, and it's hard to map this with Kubernetes. So let's put an example. Let's show how it looks a Kubernetes cluster from a high view. Like this would be the schema, like the type of different resources that are created in your cloud provider. So we have the known concepts in Kubernetes that are pods, deployment, services, ingress, nodes, persistent volumes. And then those terms in some way are mapped to infrastructure, right? We see here that we have a VPC normally that defines the boundaries of the infrastructure that we are going to create on the cloud. And then we have different zones, availability zones within the same data center that will also wrap where resources are going to be placed. And then within these zones, we have machines that will run our containers. We have load balancers. We have different cloud provider services. And all these resources in some way are going to result in cost for us, right? And Kubernetes has different ways that can help you to deal with this cost. So yeah, we are going to start seeing how we can do that. This is kind of a clumsy way to map those, but just to give you a map view of how these terms on Kubernetes can map with the infrastructure, I put this table where you see machines. So node groups are related to nodes and pods. And this is kind of the computation part. Load balancers will be the equality of service or ingress in Kubernetes terms. And for the storage, we have persistent volumes and claims, right? So starting with the core measures, what we can do to control the cost drivers that we have just seen, like the computation, the traffic, the network, and the storage. So first of all, let's start with the computation. And to understand really how this can manage from the Kubernetes point of view, we need to understand how the resources are allocated or are placed in Kubernetes. What we have in Kubernetes is the concept of node, and this node has attached some different resources depending on where it's running, right? And this is something that you choose. There is what we call capacity that will define the amount of CPU or bar CPU memory, things like storage or local storage, number of pods that can run this machine. This is a hard limit in Kubernetes that you define. And this is what the machine, the virtual machine, the instance gives to you. But we have to discount, or we have to subtract from it all the resources that are consumed by the system components or by the kube components that will run in these machines. So at the end, you will end up with something that in Kubernetes is called allocatable, which is the amount of these resources that are available to your application pods. From that point, you have to define the request that the resources request that your application are going to use. We are excluding the limits here because we are not interested on how to manage the limits. It's more interested to focus on the request. This is the concept at the end that Kubernetes used to be able to place the pods into the nodes. And the type of resources request, or the resources in general, a pod can define are CPU, memory, GPU, heap pages, different type of resources that it will need, right, to run your code. With these request resources, the scheduler is going to take care of fitting these pods into the nodes. That's why this is really important. The scheduler doesn't care if the usage is really used or not by these pods. It's just all about the request. So if we see an example here, we see two nodes. This is for the sake of simplicity. I just choose two nodes. They are the same. They are part of the same node pool, or they have the same type of resources for cores and 16 gigabits. And we have three applications. These three applications have different requests. So app 1 has 3 cores and 4 gigabytes. Application 2 has 1 core and 1 gigabyte, and application 3 has 1 and 6 gigabytes. And we see that they are mapped into the nodes differently. So in the first node, we see app 1 is consuming 3 cores already of the node, and there is only one spot free for app 2 or app 3 because they already request one core. We will kind of lose some of the resources that the node give us, right? Because we are mostly not using memory, or we are leaving like 10 gigabytes of memory out of use. So that's something we are losing. And we are paying for, because at the end, cloud providers doesn't care if you are using or not the resources. They are going to invoice you the entire instance, right? And in the scenario of the node 2, we see instead that the app 2, app 3 are filling it mostly all the resources of the node. So ideally, that's the scenario that we would like to reach, right? So trying to use as much as possible from the allocatable resources on our nodes. So how we do that? We have to be really careful when we choose the right machine instance, the right machine or instance type. And they will at the end result on how many machines we need, and how these applications are going to be distributed on the node. So granularity, we will have enough 100 pods in a node, or just 3 or 4. It has different consequences, but not only in terms of cost, it's also in terms of how to manage these nodes, right? So that's something that Kubernetes helps you, because you can start choosing one instance type and see how your applications are scheduled, and if this is enough or not for you, or if you are wasting some resources that with a different type of instance that has more CPU than memory, or more memory than CPU, will help to have a more balanced usage. And as I said before, we have to count with the resources of each node. And it's not only the system reserve FQ component, also all the daemon sets that are running in the cluster. Okay, things like login or observability. Pods that run in all the nodes will remove us from using some of the resources available on the node. So at the end, we have to do some maths and see how much of these components, how much of this capacity we will have free for running our containers. And then based on that and the size of our bigger application and how it will develop with time, we have to select an instance type. And as I said before, it's something we can learn with the practice. We will see in the next slides, but we have to rely on the autoscaling. This is the whole point of Kubernetes, or one of the most important points. It gives you a way to control the scaling up and down easy. It has a nice pre-built-in concepts that will help you to manage. We will see later. Also, another thing to consider is you don't have to use a unique node pool and a unique instance type. You can define different node pools that will contain different instance type based on the type of applications, right? So you have applications that are CPU bound or memory bound, or they need GPUs or heap pages. You can create different node pools, and you can schedule your applications in different node pools. So you really map ideally the available resources to the profile of your applications. And then lately, we have namespaces. That is really a known concept in Kubernetes, but within this namespace is something that helps you to control how many resources, how many computation resources our applications will use. It's resource quotas and limit ranges. So how many CPUs or how many memories our application are going to use within a namespace, or what will be the defaults or the maximum number of resources a certain container can require from Kubernetes, from our clusters. So let's start with the autoscaling. There's different ways to scale within Kubernetes. The first one will be the horizontal pod autoscaler. So scaling horizontally. So it creates or remove replicas on the cluster based on a certain type of usage or resource. It can leverage on metrics that are coming from the internal API, or you can put something like Prometheus or any kind of metric endpoint that is compliant. And then you can define, like you are seeing here, how it's going to behave, this controller, right? So, for example, for our deployment, my app, we want to have a minimum number of replicas of 1, a maximum of 10. And the average utilization across all the pods, all the containers, we want to not go further of 70% in this case, right? So this controller will scale up and down the number of replicas to meet our desired utilization, and that will obviously incur in having more or less consuming resources in the cluster. But it's not the only way. You can also scale vertically, so you can change the resources on a system and deployment to like kind of not to fill properly all the instance. Like if you have room to scale it within the same instance, you can leverage on this autoscaler and the recommendation that this giving you to really fit better the allocatable resources that you have in your node pools. And the vertical pod autoscaler, what it's doing at the end is measuring the historically data, the CPU and memory that your application are using, and it's going to recommend you what is the value that you should use, right? It could automatically update your resources, but if you are already using our extended pod autoscaler, it's not a good idea because there are certain scenarios where they can fight between them, and you can have undesired effects on how the application at the end is behaving. So ideally, my advice will be use vertical pod autoscaler as recommender, like a way to get what are the exact resources I want to set in my resources, in my application, sorry. And then lately we have the cluster autoscaler, so the scaling of the nodes, adding or removing nodes from our node pools. How the community cluster autoscaler works is it leverages on the scheduler. So as soon as there is a pending pod on the cluster, the autoscaler will add a new node in a certain pool. See, if you have several pools, it will use something that is called a expander to decide which one is going to choose. There's different type of expanders like list west, priority, or price. And depending on that, it will choose one or the other pool. If you set, for example, price, which is available in Google, it will take care of trying to add the less cost as possible. In list west, it will try to take an output that will waste the less resources as possible. Priority is something that you can select. So yeah, you have different possibilities here on how to decide how the autoscaler will grow your cluster. The same for going down. The autoscaler, when you define a threshold, which is kind of important and something you have to experiment with, which is the threshold which from where the autoscaler will go down in nodes, and then yeah, it will drain the system node to move running applications to other nodes that are not filled. So the combination of these are can be the perfect automation to try at the end to fill our nodes to the very top and not leaving any resource pending. So that's the ideal. And this is something obviously that you have to monitor and you have to learn with the experience. And in this image, I kind of collect the three types of scaling. We see that, for example, our horizontal pod autoscaler is adding a new application which has not fit in any of the nodes. So the cluster autoscaler is aware of this app to not having a place to run, and then it's adding a new node. And at the same time, we have a vertical scaling there, which is giving us recommendations of which application resources you have to set for example, in this case, the app one. And then you will review these recommendations and update the values. Other computation topic that we can rely on to save cost is preemptible instances, or what is called in some cloud providers spot instances. And at the end, these are the instance, so this is the resources that are sparse in the data centers of our cloud providers. So they make use of these sparse resources, giving us substantial discounts to use them. But the drawback is that at any time, like within 30, 150 seconds, depending on the cloud provider, they can claim back the resource, the instance. So that's not ideal to run whatever type of application, but things like batch jobs or light applications that are not in the critical data path of your business, that could be ideal, because as I say, that the savings could live between 60 and 80% of cost comparison with standard instances. So the cool thing of Kubernetes is that you can combine the standard on-demand instances with these preemptible instances. And then you can set up scenarios where if there is no enough resources available in these spot instances, you can fall back into on-demand instance, right? Something important to consider is your application should be kind of architecture to run in Kubernetes, but especially in this type of instances, because at the end they have to first be able to shut down covertly, so they don't leave requests on the middle, or they don't do work that can be not idempotent. And at the end, also they have to have some settings like bot distraction budgets or others. So you at least you have always some replicas available in the cluster, even if they are in these on-demand instances. So that's something you have to learn, because it will depend a lot on the type of application that you have. Then something which is between computation and network is the cluster composition. And at the end is how do you segregate your applications by cluster. So with all these managed solutions, Kubernetes solutions, create clusters nowadays is not really difficult. Like within 15, 20 minutes, you can have any cluster, which is awesome, because then you don't have to, provision by yourself and configure entirely the cluster from scratch every time that you want to have any cluster. Is quite automated, and companies like the one that I'm working for, they are giving a really nice UX to start these new clusters. But then there is a new whole setup of concerns that pop up, which is how should I split my applications, right? Now I can create like a cluster by environment or by team or area, or as usually the people years ago was doing. You can still create one cluster and rely on multi-tenants principles that Kubernetes gives you. But all of them has pros and cons. And you need to understand what are also the implications on cost, right? There will be costs that are associated with having a unique cluster that are related with the numbers of nodes and node pools that will have to grow, and how to manage a big cluster is also something that you have to be careful. But at the end, if you are also creating a lot of clusters, you can face then other cost drivers, like the incurring cost with control planes or managed solutions, like they input you cost based on clusters spend, so the number of clusters that you have. And also because at the end, if you have to interconnect or you have to connect services between clusters, and you need to route traffic between different zones or using load balancers to route flexible the traffic from a service to the other that is from one service to the other that is running a different cluster, then that will be added cost in comparison with running the service in the same cluster, right? So that's something to take into account. My advice is if you have a service or application that need to talk with other service extensively, I will always put it in the same cluster. So that's something we have learned from customers. And then something about how you split node pools, how you create node pools, because at the end, one of the reasons to go with clouds is the easiness of deploy your applications in different zones and be reliable even if there is an outage in one of the data centers, right? But there is also a cool count with an extra cost in terms of egress traffic. So usually cloud providers invoice you by the amount of bytes that you move between different zones. So not always you need to put your applications in different zones. That obviously depends how reliable it needs to be, which will be the CLA of your application. But most of the occasion, if you run Kubernetes or you run a system where you can spin up containers in different zones quickly, if one of the zones go down, then you have to consider if it's worth it or not. So there is also something important, which is you have to set a node pool per availability zone. So you could create a node pool across different availability zones, but then for the autoscaling, it will be hard, the automation, to decide which how to spin up a new node in which zone, because usually the zones are related to the node pool. So the advice here is use a node pool by zone and don't mix the instance type, because you have to have a consistent pool of resources and computing resources, and mixing this up, it will make hard also to the scaling part. So I will advise always to use the same type of instance across your node pool. Something about network pools, network policies. This is not really related with cost, but it can help in the way that you can limit the traffic that is going out and in the namespace. So you can define which, by default, the night policies and control that your applications are not connecting with anything. So at the end, it's a way to control who is going to talk to, and then based on that, you are aware of these connections. There is also the Ingress services. So the Ingress services are mapped with the load balancers, right? And there is kind of two ways to expose your traffic. One is via the Ingress controller. So the Ingress controller is a component that will run in some of the, as a deployment in some of the nodes, and it will provision a load balancer. And then you will decide, or your teams will decide based on Ingress, how the traffic will be flowing from the load balancer to your services. And that's great because you are kind of managing a single load balancer. And if you compare with creating a service type balancer for every of your applications, in terms of cost, it will be much cheaper, right? So normally load balancers are invoiced by traffic, but also by entity, by instance. So that will be something to consider. There is some pros and cons on using one and the other. Like if you use service type load balancer for everything, obviously you will be isolated in terms of nothing will impact your applications. If one of these applications is behaving where or there is a DNS attack, it's going to just go against one load balancer, right? So there is kind of isolation or reliability attached to this approach, but at the same time you are probably wasting resources. So at the end, my advice is you have to use Ingress controller, and if you are using different type of applications and then use different type of SLIs, probably you will end up using different Ingress controllers even if you run in the same cluster. Okay, now we go to the storage part. So yeah, there is different type of storage classes in the cloud providers, right? And that will give you different IOPS or throughput. But what is important here is with Kubernetes, you can define how big will be your volumes. Like you will be able to decide on the fly dynamically what will be the size, and you can resize that. So most of the cloud providers give you the possibility to increase the size of the volume after it is created and reloaded the pod with a new volume. So starting with small volumes and then growing up as is needed is a nice way to also save some money. Then we can also automate volume snapshot. So in case that your application has to not be running 100% of the time, then you could take volume snapshots and then recover from this snapshot when you have to redo the job. So like batch processing. And then also you can rely on the ephemeral storage that is provisioned within the instance of the cloud provider use for the Kubernetes nodes, right? That's also something to consider, and you can also limit based on that your applications. Now Kubernetes gives you the possibility to request storage of the ephemeral volumes that are attached to the instance. Then for the file and object storage, the providers are implementing CI solutions. So for example, AWS allows you to provision EFS volumes. There is also controllers to manage S3 buckets. Same for GCP. Okay, and then there's solutions like Mini or Rock, which gives you an abstraction upon this different type of storage, and also can help you to run everything within the cluster and not rely on the cloud provider solution. And even it can give you cost in terms of management. Probably will be cheaper than use the service gives you by the provider. So it's something you have to compare and see what is worth it. Also here I pointed that the important thing is you have to manage the data lifecycle. Most of the occasions we are seeing volumes that are not used in the provider, so buckets filled with objects that they don't need it. There is no compliance or something that they need to be there. It's just the people forget to remove it. So this is something you have to tackle. Yeah. And then the last part here is I wanted to show you that Kubernetes gives you the possibility of labeling, as you know. But the cool thing of labeling is that most of the solutions out of there are aware of this labeling and can help you with the charging back of the applications and resources used by these applications to your teams. So you can relate cost directly the infrastructure from MSpace to a team and know how much money is spending one team. There is something which is shared resources, which they are more difficult to account for how to split them over teams, but there are different solutions for tackle that. The same for managed services. So most of the occasions you are using also some managed service on the provider. Most of them, they give you the possibility to tag. So another ideal action here will be use the same tagging, and at the end you can relate all this information together. So let's talk a bit about trade-offs. I'm going a bit late on time, but I will try to cover. So everything has a price, right? Kubernetes enables you to make some of the things that were hard in the past really easy. Like Kant gives you the possibility to change instance or to prove a new type of instance type in your clusters. But it has a cost, and mainly all the cloud providers are giving you saving plans or big discounts if you reserve in advance the instance that you are going to use. So at the end, if you want to get profit of these discounts, you have to commit with the cloud provider. And then this instance flexibility is kind of lost, right? So you have to probably deal with both sides, the best of the both sides. Then the autoscaling part, like it's great. As I showed you, how flexible can be a cluster, right? How can scale in different directions? How can accommodate to the different traffic patterns that you will have? But it comes with a lack of control, right? Sometimes you don't know how it's going to act your application if there is suddenly a peak of traffic at a certain time. And the scale, the horizontal pod scale, for example, is not enough to cope up with or your application is not really, able to cope up with this scale. And so that's something you have to take care of, and really keep an eye on that. And then the isolation of reliability. So yeah, things like namespaces or container isolation. It gives you a nice limits to rely on for most of the business. But it also comes with redundancy, right? At the end, you have to run some shared components for all your containers that maybe in other scenarios you will don't have to do it, right? Then the scalability and powerfulness of Kubernetes, as we have seen, like you can create clusters as big as you want in theory, but at the end you have to account for of the resources that come back, that the infrastructure that is back of the resources are charging you back, right? So the teams has to be aware of this cost and be aware of the resources that they create in the clusters and account for it, right? Then there is kind of a low entry barrier. Like now it's kind of easy to create a cluster in a managed service and kind of learn the few principles of Kubernetes. But then there is a steep learning curve to really manage and to control all the features, functionality, and different scenarios that a live production business can occasionate in a real scenario, right? Then there is a huge ecosystem around Cloud Native and Kubernetes, which make it quite easy to deploy new tooling in your clusters, but it comes with a complexity because you can deploy or deploying something to your system is not meaning that the work is done. You have to maintain it, you have to upgrade it, and there should be a team that is owning this deployment and is managing and is customizing. And at the end, these are cost related with this tooling that is deployed there. So you have to also check carefully what things you put in your clusters. So now I wanted to finalize giving you some tooling there are in Cloud Native landscape that can help you with the cost. There is a huge number of different observability and monitoring stacks out of there. I'm not going to advocate for any of those in particular, but most of them they are moving to the same direction. You can track the different consume in terms of resources, storage, or network that your applications are using, and then based on that, you can relate with the batch and that you have and the cost that are charging from the provider. So yeah, that's something really to take an eye. And then, as you have, I've seen at the beginning, you are already using some cost management tools. Indeed, there is some nice solutions there out of there, which are really doing this work of correlation, like taking the resources that you are using in the cloud provider, which are aware of Kubernetes, like deployment pods or volumes, persistent volumes, and map those to the cloud provider expenses. So you don't have to do this matching, like creating your own cost management tool. It's something that this tooling is doing for you, like this correlation. So at the end, based on the labeling that you are adding to your resources, you can know this team, this project is that expensive, right? Here I put things like Kaboom, which is a tool for load testing, because as I said at the beginning, the resources is quite one of the hot topics in Kubernetes, how to define your resources. So Kaboom lets you to perform easily in a Kubernetes native way load testing on your applications and see how your application develops with traffic, with different scenarios, and then based on that you can start setting the resources. And then you have something which is called the logs, which at the end is the vertical pod autoscaler, but with an interface. And it's a nice dashboard to see how many resources, what that will be the ideal resources that your application should set into the manifest based on the observations that the vertical pod autoscaler takes from the cluster. So that's also nice to take a look. And then we have special scenarios where we are having event-driven system, and we have a bunch of workers that will make some jobs based on events. And for these scenarios, things like KEDA, which is a scheduler based on events, will help you a lot because it will spawn applications based on the number of events that you have. So you don't have to have idle workers waiting for events. It will manage for you based on different configuration, and it's also nice to check out. And then lastly, I wanted to put Janitor and Kubernetes Autoscaler, which are just tools especially interested for development and staging scenarios, which lets you to, for example, decide to scale down all the deployments in your development cluster, or clean a deployment after a certain time of that has been deployed, the deployment. So yeah, take a look if you are running test or the applications in places where you don't need a high availability across all the day. And that's all. Thanks everyone. If anyone has a question, just so that.